invite to continue here based on Julia's talk. So we already talked a lot about the second largest component, about cluster size decay, and we'll continue on large deviations of the largest cluster in random graphs. This is also joint work, of course, with Dieter, who is in Chile. So we started this very brief recap. So what we see here is, again, a realization, the same one as Julia showed, of Bernoulli bond percolation on ZD. And we saw that the behavior of small clusters, so the cluster containing the origin or the second largest component, was driven by surface tension, the size of the surface of an n-dimensional ball. Because if all the edges sort of crossing this boundary, the outer boundary of a cluster, are absent, then that's the best way to make clusters small. So we see stretch exponential decay of the cluster being in a component bigger than k. The second largest component is polylogarithmic with exponent 1 over this zeta. And now we'll discuss the size of the largest component here, which is always blue in my slides. So we assume that the model is supercritical, which is again the theta p. And what is a result by Pistoia is that the probability that this largest component is much smaller than you would actually expect. So smaller than theta minus some epsilon. And also decays stretched exponentially in n with the same exponent. So again, the best way to make the largest component very small is by excluding all the edges on the outer boundary of a cluster here. But on the other hand, you can also look at the event that the largest component is much larger than you would actually expect. And that probability doesn't decay stretched exponentially, but it decays exponentially in n. And the reason for that is that you really have to open up linearly many more edges in the graph to make the giant much larger than you would expect, which comes at an exponential cost. So the decay of the upper tail, we say, is much faster than the decay of the lower tail. That's also visualized here. Now we'll continue with the models that Julia introduced, so long-range percolation and geometric inhomogeneous random graphs. And we're interested in the question, is it still true that the vertex boundary plays an important role for the lower tail? And secondly, is it also still true that this upper tail decays much faster than the lower tail? So a brief recap of the models. So long-range percolation we can perform as follows. So here I will do it on ZT, but you can also do it on a Poisson point process again. So here we have a box of volume n. Look at the points, and to determine the probability that an edge is present in the graph, we look at the distance between two vertices. We want that far away points are less likely to be connected, so we take 1 over the distance raised to the dimension d. Then we have a long-range parameter alpha, and again, large values of alpha lead to fewer long-range edges. We take it bigger than 1 to ensure that the graph is locally finite. Then we have an edge density parameter beta, which is positive, or we also call it the spread out parameter. So large values of beta lead to more edges in the graph. And we chop this off at 1, and then we get a graph that looks like this. And now you may notice one difference with the model that Julia introduced. That's the parameter P, which is a percolation parameter. So given this graph that we see here, we now keep each edge with probability P and remove it otherwise. So this is the resulting graph that we get at the end. And now for this talk, we will be interested in the size of the largest connected component, blue component in this graph. So how do we get a geometric inhomogeneous random graph? So I call it here kernel-based spatial random graph as in the paper, and GX are just a special case of that model. So we start now with a vertex set where each vertex has a spatial location and an IID weight, which we will assume to be a power law. And here you see the two-dimensional case, where we look from above and the radius of each vertex corresponds to its weight. But sometimes I will also draw it like this, where the model is one-dimensional and the height of a vertex corresponds to its weight. Now we have, again, the same parameters as for long-range percolation. So we have a long-range parameter that controls the number of long edges, an edge density parameter, and a percolation parameter. But instead of having this probability here on the left, we now need to include a function of the weights, and we will take this to be the product of the two weights. If we sample the edges using this probability conditionally in all the locations and the weights, this is the graph that we see. So in 2 dimensions, this is the graph that we get. So let me try to summarize our result for large deviations of the largest connected components in those graphs. So we assume supercriticality again in this one single slide. So for the lower tail, so the probability of observing a much smaller giant than you would actually expect, we can prove under the assumption that the vertex boundary of a box, sorry, that's not correct. So the number of edges of leaving a box of volume n, if that tends to infinity, the long edges, then we can prove some results. So the first result is that for long-range percolation, we can again prove that the probability of observing a small cluster decays exponentially in the size of the vertex boundary. So here my wiggly sign means up to constants here in the exponents. And this is true for both models. So that means that for long-range percolation, we see two competing effects. On the one hand, we have the surface tension term, which is n to the d minus 1 over d. On the other hand, we also have a long edge term, which corresponds to long edges between low marked vertices very far away, order n to the 1 over d. And for gigs, we see a third term appearing, which is exactly the zeta that Julia discussed in the previous talk. And a small remark is that this is true up to some log correction factors when these exponents are actually equal to each other. And then sometimes we have log factors in the lower bound that we don't prove yet in the upper bound. We think that our lower bounds are sharp. So how does this compare to some previous results? So for long-range percolation, it was known by results like Biskup, that the probability that the giant, the largest connected component, is smaller than epsilon times n, decays stretched exponentially. And here also this 2 minus alpha pops up, but there is still a minus little o1 term, so can basically almost get the bound that we see here on the left, but not exactly. It's a tiny bit looser. And also big difference is that here this epsilon has to be very small. It's a small constant, and we don't know if we can increase it up all the way to the percolation probability theta. That's an extension of this result.
And in the first yes. case, epsilon also is small. In the first slide, in the first line, yeah, the first line, yeah.
Yes, epsilon is small.
Okay.
This is for arbitrary epsilon positive. Of course, there will be some constants here in the exponent popping up that depend on epsilon. Also on the bottom. So when we were actually writing down this paper, there was another paper that appeared on the archive, and which is covering a special case, namely the one-dimensional case where there is no percolation parameter, so p is equal to 1. There are also no really long-range edges, and they prove a very similar result to Biskup's one. So the probability of having the largest component smaller than epsilon times n is at most decaying stretched exponentially with the same exponent as we have. So if you take here on the left alpha to infinity, then you get exactly the decay that we see here on the right. And again, a main difference is that here this is for epsilon sufficiently small, and this result on the left is for any epsilon positive. So let's go to the upper tail. So this is the probability of observing a much larger cluster than you would actually expect. And I want to do a very small poll. I'm not sure if it's possible, but otherwise we can put, I guess, reactions. So maybe let's have a question. So would you expect that for long-range percolation, so if we have some very long edges in the graph, would you expect that this upper tail decays as fast as in the nearest neighbor percolation case, or maybe faster or slower? And I want to put a smiling emoticon maybe for slower decay, and a sad emoticon for faster decay or exponential decay. Or maybe do like a 5-second vote here. I don't see any reactions anywhere. So, okay, let me just give you the spoiler answer. So the decay is going to be exponential again in the long-range percolation model. Now for the GERC, so for cases where there's a lot of degree inhomogeneity, it's going to be completely different. And what we see is that instead of having a faster decay of the upper tail, decay is actually much slower than the decay of the lower tail. So instead of an exponential decay, we observe a polynomial decay of the upper tail. And I have to remark here that this is only true at sort of the continuity points of a function I rho that we explicitly identify. And I hope to discuss this function I rho at the end of the talk. So here, this sim sign doesn't, it means up to a constant factor here in front, so like real theta. So for the remainder of the talk,
what is I overall? I overall, what is it?
So it's a function of rho for rho bigger than theta, and I will give it at the end of the talk. I will give you the definition of the function, but it's basically describing. So if rho is much bigger than theta, then it's of course much more unlikely to see a large component larger than rho times n. So we'll tend to infinity as rho tends to 1. And we find the exact formula for this in terms of the generating function of the cluster size distribution. We'll see it at the end.
Thank you.
So this is my plan for the remainder of the talk. So first I want to say something about the lower tail of large deviations. So why is now the exponent 2 minus alpha popping up there for long-range percolation? And after that, I'll say something about the upper tail for GERT. So here, I guess this slide is sort of an overview of what Julia discussed so far and what I'm discussing, and it sort of connects all the different topics in our talks. So if you want to prove the lower bound on the lower tail of large deviations, or an upper bound, then we first need good control on probability of having a cluster of size epsilon n, where epsilon is very small. So we can show first using renormalization methods that this decays as e to the minus n to the zeta. Then based on that, we can, for example, using methods that Julia explained, an upper bound on the second largest component. From there, while using truncation methods, we can go to the cluster size decay. And by using local convergence, we can then extend this to a law of large numbers for the size of the largest connected component in this graph. And now this is sort of the last ingredient that we need to extend to go to the lower tail of large deviations, where this epsilon here can really be replaced by theta minus epsilon. So how to do this? So we'll look at the one-dimensional model. So this red box is a box of volume n, and the height is just something to illustrate the weights, but we don't really care about the weights in this example. And what we saw from a computation that Julia did is that we expect that in this volume n box, there are about theta n to the 2 minus alpha vertices that have a very long edge, meaning of length n to the 1 over d, and in dimension 1 this is just of length n. And we'll show how this Laplace numbers implies this result. So now if we divide this box of volume n into smaller boxes, and what should this box size to be exactly so big that each box contains with positive probability or probability close to 1 an edge, a vertex incident to an edge of length n, let's say. Then we get in total n to the 2 minus alpha boxes. So roughly each box here is incident to 1 long edge. So the size of a box corresponds to n to the alpha minus. Now let's look at the induced subgraphs in those boxes. And because we have this law of large numbers, we can assume that n is very large, so that in a single box, the probability of having the 2 small largest components, so this is sort of a local giant, is extremely small. Let's say smaller than epsilon over 2. Now, just by Chernoff bounds, the probability of having more than epsilon times the number of boxes without a giant decays exponentially in the number of boxes. So that means that we see exponential decay with exactly the right exponent, n to the 2 minus alpha. Now let's do a small computation. What's the probability that 2 local giants in those boxes are connected by an edge? So both giants contain roughly n to the alpha minus 1 many vertices. So the total number of possible edges is n to the alpha minus 1 times n to the alpha minus 1. And since the distance between 2 vertices is at most m, we can use a lower bound for the connection probability of 2 vertices, which is n to the minus alpha. What we see is that this is equal to n to the minus 2 minus alpha. So similarly to what we saw for Julia in the Gür case, is that this is bigger than any constant lambda over the number of boxes. And this lambda here can tune by tuning the box size appropriately. So this is a summary. So now we can use large deviation principle for the size of the largest connected component in Erdős-Renyi random graphs. So that gives this result here. So the probability that the giant in Erdős-Renyi random graphs has size smaller than rho lambda, which is sort of rho lambda times m, sorry, minus epsilon m, decays exponentially in the number of vertices that we have. And here this rho lambda is really the survival probability of a Poisson lambda branching process. And if we make lambda very large, then this rho lambda, the survival probability tends to 1. And so we can make sure that the connected component that we are constructing really contains almost all of the boxes that we see here in the graph, and that we can find here this result on the top, namely an upper bound on the lower tail of large deviations.
Giants connects, probability of giants connect. What means giants connect?
So okay, so giants, you should think of giants as being a local giant. So that's one dark red blob. And each dark red blob is sort of an induced subgraph in a box. And this is a connected component in this box. And this is a local giant. And then here on the left, we have with probability at least 1 minus epsilon.
No. The probability giants connect. What connect? What with what connect?
Okay, so these are two. So giants you should think of as a set of vertices in a connected component in one of those red blocks. So this is a connected component in this subgraph here in a box. And now I look at the largest connected component inside this box. And that I call a local giant.
Mm-hmm. Mm-hmm.
Does that make sense?
Thank you.
Okay, so we have, so here this is the, this n to the alpha minus 1 is really roughly the number of vertices in a local giant. So the probability that there exist vertices in those local giants that are connected by an edge is roughly 1 over n to the 2 minus alpha. And this we can then use for the large deviation principle of the Van Van graph. So this explains why we do see sort of here a 2 minus alpha. Now to extend this to get this d minus 1 over d here in the first place, you can use renormalization to nearest neighbor percolation on ZD. But to make this work, you really need to assume that the number of long edges from a box, long meaning of order n to the 1 over d, tends to infinity. There's a small problematic region where we don't have this limit tending to infinity, but where the model can still be supercritical. In that case, we don't know exactly what is happening. And the argument for GERDs, so here where we have also a 3 minus tau over 2 minus tau minus 1 of alpha, uses a very similar argument to what I described before, except that we don't look at edges between low mark vertices in those local giants, but we can ensure that vertices of weight n to the gamma, those very special vertices from the previous talk, are connected with constant probability to another vertex of weight n to the gamma. So we only consider edges between those very high weight or high mark vertices. That's the main difference there. So now let me continue with the upper tail, which is the probability of observing a much bigger giant than you would actually expect. And for nearest neighbor percolation, we know that it decays exponentially. For long range percolation, we can also show that this decays exponentially. But here in the inhomogeneous degree case, it decays polynomially. And I hope to explain now this, this function I rho that we see there. So what we can prove is that this function I rho has the following formula. So probability of observing a giant bigger than rho times n, where rho is of course bigger than theta, decays as n to the minus tau minus 2 times some function of rho. And so here tau is, remember that this is describing the inhomogeneity of the weights. So this is the Pauli exponent of the weights and also describing the decay of the degree distribution. So this is the formula for the knot h of rho. So we define a different function, capital H C, which is the generating function of the cluster containing the origin. So really the green cluster here in the picture. And now h of rho is the absolute value of the log of the inverse of the generating function evaluated at 1 minus rho divided by the absolute value of log 1 minus p. And this may look very mysterious, but I think there's quite an intuitive explanation for this. So this h of rho and then rounded above describes the number of hubs in the graph, and hubs are vertices with weight linear in n that are required to increase the size of the giant from roughly theta n to at least rho n. So you think of it as follows. So let's first look at the subgraph on lower weight vertices than theta n. Then we have a giant, which is going to be roughly of size theta times n. And then we add the hubs on top and look at all the edges to the graph that was there before. And then the size of the giant increases from theta to rho. And why is this order n weight so important? Well, here on the left, if we look at the connection probability, so if we plug in n for one of the weights, and we divide by the maximal distance in the graph, which is n to the 1 over d, raised to the power d, then the n cancels. And so that means that hubs always connect with constant probability to any vertex in the graph, no matter where it is. So then my claim is that this is really the right strategy to increase the size of the giant. And this will give you the decay that we see here on the right. So the probability that you observe h vertices with weight roughly theta n is as follows. So vertices have independent weights. So that means that we have roughly n vertices, and the probability that we see h rho rounded above vertices weight at least n is binomially distributed with these parameters. So now we can substitute the weight distribution. So this probability is equal to n to the minus tau minus 1, by just integrating it out. And this is a very simple computation, is roughly n to the minus tau minus 2 times h of rho. So let me briefly describe some related work. So this polynomial decay can also be seen if you look, for example, at sums of power law random variables. And this is called then the principle of a single jump. But also more recently, this has been studied for other graph properties. So for example, large deviations of the number of edges, En, has been studied in a very recent paper by Pim van der Hoorn, actually. I'm not sure if he's still here. Remco van Hofstad, Link Ryu, Peter Mertens, and Eladri Maitra. And they prove that a large deviation principle for the number of edges and the probability that you see n times new expected n times new edges more than you would expect decays as a certain constant times n to the minus tau minus 2. Then again, you see here this mu, but then rounded above. And another similar result is a paper that I'm currently about to finish with Bert Zwart. And there we also study the size of the largest math component, but then in non-spatial random graphs, where we see a very similar decay as what we see here above, except that we can especially identify this constant C rho. We don't have this steep annotation here. So in all those three examples, we see that we are rounding above a certain number. And this is because it sort of describes the number of hubs and the number of vertices that you need to increase either the number of edges or the size of the giant. And if this number of hubs is exactly an integer, we don't know what is happening precisely. Is it like exactly that value or one more or one less? And that's why we can only prove these results in this form for the continuity points of these rounded functions. And what we also see is that here, for example, for the number of edges, this rate function, so minus tau minus 2 times u, increases linearly in nu, sort of the axis edges that you require in the graph. While this function h rho has a very different asymptotic behavior. If you would look, for example, in the limit as rho tends to 1 can of course only become 1 because there are at most n vertices in the graph, then this behaves as log of 1 over 1 minus rho. So why does this generating function here pop up in the we call rate function of this problem? So instead of looking at the giant, I want to look at the complement of the giant. So n minus the size of the giant. And my claim is that if we now reveal the graph in 2 stages, so first we look at the number of the giant, the graph without any of the hubs, and then we add the hubs on top and look at what this changes to the graph. Then this complement of the giant is roughly all vertices that are in a component that does not connect to the hubs. So we sum over the component sizes, which is L here. Then we sum over all components in the graph without the hubs that have size at least L. Now, each vertex, each component of size L contains L vertices. And then here we have an indicator that our component does not connect to the hubs. So let's try to see if we can massage this formula a bit. So now we're adding the hubs to the graph. And what is now the probability that a component of size L does not connect to one of our H hubs? Well, if we look at the connection probability here on the left, then each edge between a vertex in the component and any of the H hubs is absent with probability 1 minus p. They all need to be absent to realize this event. So this is really 1 minus p raised to the size of the component times the number of hubs. So let's approximate this indicator here with the expectation, and then this is what we get. So now we need to make sense of the sums that we see. So let's look at the number of vertices that is in a component of size L in the graph without hubs. And typically these hubs are of course not present in the graph. So that means that you can basically look at typical realizations of the graph and see how often it occurs in such graphs that a vertex is in a component of size L. And using local convergence theory, you can prove that this actually converges to the probability that a special vertex at the origin is in a component of size L. This is really the property of local convergence. And luckily, the graph that we consider here converges locally to its infinite version. So meaning the case where we don't look at the graph just inside the box, but really in the infinite RD. So what does this mean for the number of components of size L in the graph without hubs? Well, each component of size L contains exactly L vertices. So the number of components of size L should be a factor L smaller. And we get here this. So if you want to use this in our formula above, then we'll approximate the number of components of size L by n over L times the probability that the origin is a component of size L. So now let's consider again the proportion of vertices that is in the giant. Now, if we substitute this n over L times the probability that the origin is a component of size L into the formula here, then we see that the L actually cancels nicely. The n cancels because of the division that we have here. So we get exactly the sum over L at least 1 minus p to the LH times the probability that the origin is in a component of size L. And if you look at this formula, this is exactly the generating function of the cluster containing the origin. So HC of 1 minus P. Our goal was to make giant increase from theta n to something bigger than rho times n. And it's actually the same as saying that we want the complement of the giant to decrease from 1 minus theta n to something smaller than 1 minus rho times n. So if we now compare this expression here on the right to 1 minus rho, then it's exactly here this formula that pops up at the top. So that this gives us intuition for the number of hubs that we need to increase the size of the giant from theta n to rho n. And this rounding up is needed because the number of hubs can, of course, only be an integer. Is this clear for everybody? Because I think this would be a good time for questions.
May I ask one small question?
Yes, of course.
Why is it important to raise from theta to exactly rho? Why the rho here?
So very good point. Sorry, that's not so clear maybe. So the goal is really to find the probability of the event of the giant being larger than rho times n. That's the goal, and we want now to find an event that realizes. We want to find the best strategy that realizes this event. And my claim is, and what we actually can prove, is that having exactly this h row number of hubs is the best way to increase the size of the giant to above rho times n. And any other strategy that you could come up with will have smaller probability than this this decay that we see here on the right. So the goal is to find an event that realizes the giant to be larger than rho n.
Okay, thanks.
So I think I will stop a bit earlier than expected, but I have many slides after this if you want to ask questions about specific things. So this sort of gives a very good picture, I think, of what's happening with large deviations of the giant component in our graphs. So we saw the stretch exponential decay determined by the vertex boundary for both long-range percolation, geometric inhomogeneous random graphs, Bernoulli bond percolation on ZD. But now if we look at the upper tail, then there's a big difference between degree inhomogeneous models and more degree homogeneous models, such as long-range percolation and Bernoulli bond percolation, where the exponential decay sort of changes to polynomial decay if there is degree inhomogeneity. And to prove this exponential decay here on the top, maybe let me say a few words about that, is we can again study the size of the complement of the giant. And by looking at large but constant sized boxes in our graph, we can control the number of size L components in all those boxes. And these size L components are not in the giant. So you really have to change sort of linearly many boxes locally and to make the giant much larger than you would actually expect. And this sort of gives a tiny bit of intuition why you see exponential decay here, why you see polynomial decay here. So you don't have hubs in these top models that can help you to increase the size of the giant. And that's the main difference between the two cases. Let me stop here and then we can take more time for questions if you have them. Thank you very much.
So, thank you.